let's explore gradient descent variants. So there are three major types of gradient descents: batch gradient descent, stochastic gradient descent, mini batch gradient descent. We'll see why do we need those variations. We'll talk about the main intuitions behind this. We'll do some visual comparisons and also performance comparison. So we all know about gradient descent algorithm, right? Let's do a quick recap. So we initialize the learning rate. We'll initialize some positive learning rate. We initialize t equals to 0. T is the iteration. We choose some W0. W0 is the initial weight parameters. And then it will iterate until convergence. So what is convergence? So in the data sets, we'll have data points with output, right? So yi here is the actual output, let's say. And let's say yi hat, so that is some predicted output using our model, whatever model we are using. Now we will have some loss function that will compare this actual output and predicted output. So, and that's how we will get the loss or error. So this E of Wt, this is the error or loss. Wt is the weight parameters at iteration t, and E of Wt is the error at that iteration. So what we do, we compute the gradient of this error. We update the weight parameter Wt plus 1 equals to Wt minus alpha of this gradient of this error. Then we increment the iterations. Our main target is to minimize the loss. So and that is the convergence criteria. So once we reach there, we'll return W star, that is the optimized weights, that will be the weight parameters at the last iteration. Now, how we are calculating this gradient? So that is the major factor that defines these three types of gradient descent. Before going there, let's quickly talk about the contour plot. What is a contour plot? So contour plot is a 2D graph showing 3D data. So here you see the loss graph for a model, right? Here we have minimum loss, and as we move up here we have much more loss, right? So we are plotting this 3D points into two-dimensional here. You see these circles here, these are representing points that are having same heights. So each contour line connects points with equal heights. So as we move outwards, right, so these circles, this will represent points that is having much higher heights. So we'll use this in our discussion, that's why I quickly covered this. Now let's start with batch gradient descent. What is it? So we'll have the data set, let's say x1, y1, x2, y2 till xn, yn, these n data points with the samples and the outputs, right? So we'll have some weights W, and the predicted output, let's say yi hat for all I1 to n. Now this prediction, how we are predicting, we can have much more complex model, but here I'm just for simplicity I'm considering simple linear regression. Yi hat is W0 plus W1 xi, and this is our loss function MSE, mean square error, that is EI. Yi is the actual output minus this W0 minus W1 xi. This is the loss function. How do we calculate the gradient of this loss or error function? Is basically if we just calculate gradient of this. Now loss or error per sample is, let's say, EI. So that we are calculating here, right? So total loss or error over the data set. So that will be the summation of all the errors. Gradient of the total loss will be gradient of this all the errors, summation of all the errors. So we can simplify this further. But here the gradient we are calculating, it's over all the data samples. We are taking total loss over the data set and we are calculating the gradient for the summation of all the errors. So that is batch gradient descent. So in this update, one update is based on the whole data set, and this is the true gradient because we are using all the data points for calculation. This is very stable, and if you see, this is the contour plot for the loss graph. So here we have minimum loss, and let's say we are starting from here. So we'll move towards the minimum point, and this move, you see, this is very smooth, very stable move. So this gradient we are calculating, this is very accurate, but actually it is impractical for large data sets because it will be slow and memory heavy. So if we have large data sets, we have to load the full data set into memory because we want to compute the loss over the whole data set, all data points, right? So this will be memory heavy. And when we should use this, when we will have very small data sets with convex problems, then we can use this batch gradient descent. And when we need stability over speed, then we can go for batch gradient descent. But if the data set is large, we cannot go for batch gradient descent, given that we don't have that much compute power. Next is stochastic gradient descent. Here also we have, let's say we have considering the same data set, but consider we are taking only one random sample input, that is xi. The predicted output is yi hat. Loss or error for that sample is ei. We'll compute gradient of the loss, that is with respect to only one sample. So gradient of this EW, this will be gradient of this only one ei. So we are considering error from just one sample. So one update per sample. So this update is happening one update per sample. So this gradient we calculated only with respect to one data point. So that's why we will have noisy updates because the gradients of all the points will not point to the same direction. But on an average, they point in the same direction as the true gradient. So on an average, if you compute, it will always move towards the minimum, but some points, some data point gradients might point in this direction, some data points gradient might move in this direction. But you see, from here to here, it's also moving towards this center, right? So one dimension is always moving towards the minimum, but this is just for our intuition. So we are having very fast updates, but it escapes shallow minimum as well. So shallow minimum as well, like if we have something like this, so this is a shallow minimum. So the stochastic gradient descent will have very rough movements, right? So it can bypass this shallow minimum. But of course, we will have noisy updates. So SGD or stochastic gradient descent, this states stability is for speed. So as we saw, the movements are not very stable, right? So but it's very fast because we are just considering one data sample at a time. So the gradient computation will be very fast. Best use cases when we will have very large data sets, online learning or streaming data. So when you don't have the full data set in hand for computation, right? So we're just getting one data at a time, one data sample at a time. So then stochastic gradient descent is the ultimate choice. Next, mini batch gradient descent. In mini batch gradient descent, what we do, let's say this is the data set, full data set we have. We split the data set into mini batches of size B. B can be 32, 64, 128, etc. So for each mini batch B, we'll compute the error or loss. So let's say loss or error for a sample in the batches, this EIG, we are representing it like that. And we will compute average loss or error over the mini batch. So this is over the mini batch, we are computing the average error. And then we are taking gradient of that. So this update here is one update per mini batch. We'll have many updates per epoch. What is an epoch? Epoch is going over the whole data set at a time, right? So if we have divided the data set in multiple batches, then we'll have multiple updates per epoch. Now, This is very fast, stable and GPU friendly. It actually balances speed and stability. So batch gradient descent was very stable, but it was not fast, it was slow and memory heavy. Stochastic gradient descent was very fast, but it was not stable because it was very noisy. But mini batch gradient descent is basically a compromise between these two. It is fast, it is stable and it is GPU friendly. So now why this mini batch wins? So it will have less noise than SGD or stochastic gradient descent. It is faster than batch gradient descent and it is efficient for parallel computations, because if we have split the data set into multiple batches, so we can do this calculations parallelly. We can do parallel computations for batches. So that's why this is the most commonly used method in today's life. Now quickly see the control plot once again. So for batch gradient descent, you see the movement is very smooth but very slow, because we are considering the whole large data set at a time. For stochastic gradient descent, we are just considering one data sample at a time. The movement is very noisy, right? In mini batch gradient descent, you see this is a compromise between these two. It is fast and it is smoother than stochastic gradient descent and faster than batch gradient descent. So that's why mini batch gradient descent is the most favorable choice.